In an earlier video, I talked about calculating a confidence interval for the population mean. In this video, I'm going to talk about prediction intervals for individual y values, which are related to confidence intervals, but they're a little bit different. And so prediction intervals are focused on a problem like the following. We want to predict an individual y value that's picked at random from the population. So just think for a second, does that sound like an easier or a more difficult problem than estimating the population mean? So to put this in context, let's think about the home prices. So if I'm predicting an individual home price for a particular housing market, that's quite a difficult problem because homes vary quite a lot. Some are quite inexpensive and some are very expensive. Whereas if I'm estimating a population mean, that's a slightly easier problem. I can look at a housing market and I can say, well, you know what, the average house price in this housing market is $300,000. So it's more difficult to predict than it is to estimate a mean. And it's because we're going to be less certain about our answer than we would be if we were estimating a population mean. So we're going to use the same approach as we used for confidence intervals. So in this case, we're going to calculate prediction intervals. And they're very similar to confidence intervals, but they have a larger range of uncertainty. They're wider. But they have the same general form. So remember, the form for a confidence interval was a point estimate, which is just a single number that's going to be in the middle of our interval, and then we plus minus some estimation uncertainty to get an interval. Prediction interval looks very similar, has the same point estimate in the middle, and then we plus minus prediction uncertainty, which is going to be larger than estimation uncertainty and give rise to a wider interval. So to motivate the formula that we're going to use, we're going to think about a particular model for our home prices. So the notation I'm using here is y represents the sale price, and I is just to keep track of which house in the sample I'm talking about. So I equals 1 for the first house, I equals 2 for the second house, and so on. That sale price is going to be broken up into two pieces: an overall population mean representing the average sale price, so expected value of y is going to represent the population mean, and then we're going to add on a random error e. Okay, so for expensive houses that random error will be a positive number, and for inexpensive houses that random error will be a negative number. And then we're going to think about that over the whole sample, I going from 1 all the way up to n. So we have our sample. Now we're going to imagine a new house has come onto the market, and we're going to predict the sale price for that new house. So just to distinguish it from all the other houses, we'll give it a star. So we'll say y star is the sale price for the new house, and that's going to use the same model. It'll be a population mean plus a random error e star. And if it's going to be an expensive house, e star would be positive. If it's an inexpensive house, e star would be negative. What would be our best point estimate of y star based on our sample? Well, the best estimate that we could come up with is the sample mean. So that'll be our point estimate. And so when we use this as our prediction, we'll have a prediction error that's equal to whatever the actual sale price is for this new house, y star, minus the sample mean, which we're using to estimate it. And if I substitute in my model here, y star equal to expected value of y plus e star, substitute that into this equation here, I'll get e of y plus e star minus m of y minus the sample mean. So I've just rearranged this this equation here because I want to group together E of y and my, and I want to leave E star outside over here. And the reason for that is because we could think of the difference between the population mean and the sample mean as estimation error, and then we can think of the E star as random error. So both of those sources of error give rise to variability, and it turns out that the variance of the estimation error is equal to the sample standard deviation of y squared divided by n, whereas the variance of the random error is just the sample standard deviation of y squared. We can add these two variances together to get the variance of the prediction error. The prediction error is y star minus the sample mean. So when we add these two pieces together, we get sy squared over n plus sy squared, and we can simplify that using this formula here, sy squared times 1 plus 1 over n. Let's go back to our confidence interval formula. So from a previous video we saw that that was equal to the sample mean plus or minus a t percentile times s of y divided by square root of n. The prediction interval for y star is similar, m of y plus or minus t percentile, but then this last piece, the standard error piece, comes from this variance of the prediction error here. Okay, it's the square root of that. So sy times the square root of 1 plus 1 over n. So we can see mathematically that the prediction interval for y star is wider than the confidence interval for E of y, and it's because of this extra 1 in here. Let's go through an example of calculating this. So we've got our home prices. Our sample mean is 278.603. Our sample standard deviation is 53.8656. We've seen these numbers before. Let's calculate an 80% prediction interval for y. So we can use software to find all these numbers. So here's the mean and the standard deviation, and then this is the 90th percentile of the t-distribution with 29 degrees of freedom. If you forget why we have to use the 90th percentile for an 80% interval, go back and review the video on confidence intervals, because we talked about that in that video. And so now I have all the numbers I need to plug into my formula. So here's my formula, and I just plug in all the numbers: sample mean, the percentile, the standard deviation, the sample size. If I do the calculation in R over here, I get 71.785 for the prediction uncertainty, and then if I add and subtract that to the sample mean, I get a lower bound of 206.818 and an upper bound of 350.388. Okay, and that's our interval. If you go back and review the confidence interval for the mean, you'll find it's much narrower than this. Okay, the prediction interval is always wider than the confidence interval. And to interpret this, we can say we're 80% confident, because we're doing an 80% interval, 80% confident that the sale price of an individual randomly selected home in this market will be between $207,000 and $350,000. Let's just finish by running through one last example of how to do this kind of calculation. Let's do a 90% interval. Okay, everything here is going to be the same, except instead of the 90th percentile, we're going to need the 95th percentile. So I can get that in Minitab, not Minitab, sorry, R. Slip of the tongue. 95th percentile, 1.699. And then plugging that into the formula, I get 185 0.5726 for the lower bound, and 371.6334 for the upper bound. There's a way to get these intervals in R directly, and so we set up a model using this LM function here, and price is our response variable, and in this case over here we just write the number 1 because we're gonna use this function later on when we talk about regression, but in regression we have predictors, but in this case we don't have any predictors, so we just write the number 1 here. But if we predict using this model, then we end up with, this is the sample mean, and then this is our prediction interval here. This was the what is this? This is a 95% interval, I believe. I can check. If I look at the predict function for this, yeah, the default level is 95. Okay, so this is a 95% interval, and then down here I can set the level, and so this one is a 90% interval. So the 185.5659 and the 371.6407, these were the numbers that I calculated by hand before. They're not identical because there's a little bit of round off error here. So that's prediction intervals for an individual value of y, and I've talked about how to motivate the idea of a prediction interval and the formula that we use. It has a similar format to confidence intervals for the mean, but there's a slightly different formula. The uncertainty is a little bit bigger and the interval is a little bit wider.